First up, expand 4 plus y to the half up to y cubed. Now, you'll be given this formula here. It's actually worth learning this formula. It's not too bad. There's a pattern going on as we go on up. We just raise the power by 2, divide by an extra number each time to increase the factorial, and times by your power, but minus an extra 1. So hopefully, I'd say like, yeah, try and learn that, even if it is given in the formula book. First thing to say here is it's not actually in the form 1 plus x to the n, so we've got a little bit of work to do. Factorize out the 4. This gives us a quarter for y, or I'll write it as y over 4 for the moment. And then all of this is being raised to the power of a half. I can raise each to the power of a half separately, giving me 2 times 1 plus y over 4 to the half. So now I'll put the 2 in, because otherwise I always worry I'm going to forget about it. We can replace x by y over 4 and n by a half. So I'm going to get 1 plus a half times y over 4 plus a half times minus a half over 2 factorial, which is just 2, times y over 4 squared, plus a half times minus a half times minus 3 over 2, all over 3 factorial, which I'll write as 2 times 3, times y over 4 cubed, plus dot dot dot, but I'm only interested in up to y cubed. Okay, I'll leave the 2 out for the moment. This is going to become 1 plus y over 2. No, not y over 2, y over 8. Plus, there's going to be a lot of fractions going on. Actually, it's going to be minus next. Then I've got minus 1 over 8 times 1 over 16. So 8 times 16 is 128. So it's going to be minus 1 over 128 y squared. And then here I'm going to get a double negative going on when I times these two. The 3's are going to cancel, and that's going to leave me 1 over 16 times by 1 over 64. So it's probably best, I'm just going to keep doubling until I've done it 4 times. So 64 times 2, 64 times 4, 64 times, sorry, 64 times 2, 64 times 4, 64 times 8, 64 times 16 is going to be 1024. Actually, that's also 2 to the power 10. That might have been an easier way to do it. 2 to the power 4 times 2 to the power 6. Anyway, however you get it, it's going to be 1 over 1024 y cubed. So I'm nearly there. Taking a bit of time, but we've got to do it carefully. That's going to leave us 2 plus y over 4 minus, sorry, some of them are written as fractions. Okay, I'll write it all as fractions. So a quarter y minus 1 over 64 y squared plus 1 over 512 y cubed. Right, on to part B. We've got a slightly different expansion now, and we're asked to show that it's equal to this. Now, there's a couple ways to do this question, and actually I'm going to go through them both. First way is to identify that we've actually got this expansion if y is equal to 5x plus x squared. So let y equal 5x plus x squared in part A. So this is going to equal 2 plus a quarter times 5x plus x squared. Okay, then I'm squaring this. I'm going to write it as a double bracket. Remember, I only want the terms up to and including x cubed, so I don't need to expand the whole thing. Okay, and I think I'm going to just take some parts now. So this bit here is going to become 25x squared plus x to the 4, which I can ignore, plus 5x cubed plus 5x cubed, so 10x cubed. And then this one, I can basically take this part as 25x squared plus just, actually, that's all I need, 25x squared, because then I'm timesing by this one as well. So I'm going to get 125x cubed. And all of the terms will have a higher order, so I can ignore them. So this gives me 2 plus 5 over 4x plus a quarter x squared minus 1 over 64 times each of these, so 25 over 64x squared minus 10 over 64x cubed plus 125 over 512 x cubed. Okay, and I've managed to get this one and this one. So let's just bring the other terms together. This is actually going to be, if I times top and bottom by 16, I'll get 16 over 64. So these two together are going to equal 16 over 64 x squared minus 25 over 64 x squared, which gives minus 9 over 64 x squared, which is what I wanted. And then this one here, to get it 512, I'm going to have to times through by 8. So it's actually going to equal 80 over 512 x cubed, with the minus in there as well. So these two together are 125 over 512 x cubed minus 80 over 512 x cubed, which leaves me with 45. Good. Positive 45. Yeah, and I've now got all of them, and we can be really sure we've done that correctly. So finally, just going to write it a little bit more neatly. 2 plus 5 over 4x minus 9 over 64x squared plus 45 over 512x cubed. Okay, that is our binomial expansion up to x cubed of this more complicated expression. And just before I move on, I'm actually going to go for a second method for doing this. It's quite a nice method, method 2. And rather than substituting in y equal to 5x plus x squared, we can actually factorize this expression here. We get x plus 4 times x plus 1, all raised to the power of a half, so we can actually deal with them separately. Actually, it's best to rewrite them in sort of binomial form, so like this. Now this one here, 4 plus x to the half, is actually what we calculated earlier on. It was the very first part. So it's going to be this here, but with all the y's placed by x. So that just leaves me with 1 plus x to the half, which I can expand, do this quickly. So 1 plus the half x, a bit nicer to expand, plus, actually, no, it's still going to be quite involved. It's going to be n times n minus 1, so minus the half over 2. Oh yeah, I don't have the x over 4 now. That's why it's not quite so bad. Threes cancel again. Then over here, it's going to be plus 1 over 16 x cubed. And therefore, this 4 plus 5x plus x squared, power of a half, is going to equal that first one here. You know what, this is how I did this question. And I thought it was going to be more simple, but I'm not sure it is. I think the first method is going to be actually a bit better. Because now we have to expand this. Well, sorry, not expand, multiply with this. Oh, okay, but remember, we only need to go up to x cubed, so I don't need to do all the terms. So let's multiply through by the 2. I'm not going to draw, actually, I will draw them all in, but I'm not going to do it with all of them. So 2 plus x minus a quarter x squared plus 1 over 8 x cubed. Next, I'll multiply through by a quarter x, so I'll get plus a quarter x minus 1 over 32. Wait, I missed a bit. I think I do like the lines actually. So plus a quarter x, that one I missed, plus 1 over 8 x squared minus 1 over 32 x cubed. Then I've got minus 1 over 64 x squared minus 1 over 128 x cubed. And finally, we're going to get plus 1 over 512 x cubed from that one. We can ignore all the rest because there'll be higher powers than x cubed. All right, let's bring this together to get the answer. So I've got the single 2 by itself, and I've got x plus a quarter x to give me 5 over 4x. And then let's deal carefully with the x squareds. I'm going to have a minus a quarter plus an 8 minus 1 over 64. That's all the terms with x squared in. Let's put it over a common denominator of 64, so minus 16 over 64 plus 8 over 64 minus 1 over 64. This gives 8 minus 17, so minus 9 over 64. Okay, and if you look at the answer, that is correct. Then that just leaves us with the x cubed terms. So we've got 1 over 8 minus 1 over 32 minus 1 over 128 plus 1 over 512. Common denominator of 512. So for 8, what do we need to times through by 6? No, not 16, 32, 60, 64. So it's going to be 64 over 512 minus, then this one will be 100, not 128, 250. Sorry, I'm trying to get it to be over 512. I'm just trying to think, what do I times by? 30 to 16. Yeah, it's going to be 16. So it's 16 over 512. And this one is minus 4 over 512 plus 1 over 512. That is going to give 64 minus 20, so 44. Then add on 1, 45. Okay, that is correct. Right, and I've got to say, although it seemed quite neat to factorize the expressions, the fact that we've had to times them, I think there's so much more likelihood of making a mistake here, which of course you can go back through and correct because we know the final answer. But yeah, in summary, this method 1 that we did is a lot better. But anyway, we've done part A, and now we've done part B in 2 different ways. Part C says, show that this expansion will converge for these values. Now actually, this is where my second method really comes into its own. So you can use aspects of both, because we factorized it into these 2 binomial expansions, 4 plus x and 1 plus x. Um, and then remember, I wrote the 4 plus x1 as 2 lots of 1 plus x over 4 to the half. So this one here is valid for the modulus of x less than 1, or x is between minus 1 and 1. And this one here is valid for, well, it's going to be minus 1 less than x over 4 less than 1. So it's going to be minus 4 less than x less than 4. And therefore, the whole thing will converge from minus 1 less than x, and hence also, now I've got to be honest, this number of marks absolutely baffles me. All the effort we had to do in part B, even using the first method, it's quite a bit, and this is 6 marks, but that is legit, and this works well. So that is enough. On further reflection, I think I've realized why it's 6 marks. We'd have to, if we didn't factorize it, then what we'd do is we've got the 2 outside, and then 1 plus 5x plus x squared all over 4 to the half. That's how we can rewrite it, just like I did earlier on. And so we would require that that is between minus 1 and 1. Sorry, this term here. Which would give us minus 4 less than 5x plus x squared less than 4. And we've got this sort of quadratic inequality to solve, but it's actually between these 2 values. So I'm going to go through how we do this. Just find a bit more space down here. Okay, I'm actually going to separate it into two different parts. So first up, let's look at the lower end. So if x squared plus 5x is greater than minus 4, then x squared plus 5x plus 4 will be greater than 0. Nicely, this factorizes. X plus 1, x plus 4 is greater than 0. So if I draw a quick sketch, I'm going to get roots at minus 4 and at minus 1. And it's going to be that x is greater than minus 1 or x is less than minus 4. Let's take a look at the other one. If x squared plus 5x is less than 4, then x squared plus 5x minus 4 is less than 0. Luckily, this one actually doesn't factorize. So if I set it equal to 0, I can use the quadratic formula, and this is something I've done earlier. I get minus 5 plus or minus root 41 over 2. So now if we draw this out, if we minus it, we're definitely going to get a negative. Minus 5 minus root 41 over 2. If I add it on, then root 41 is bigger than root 25, so we're going to get a positive here. So minus 5 plus root 41 over 2. And therefore, it's going to be between these two values. So for both of these to be satisfied, it's going to have to be greater than minus 1. Minus 1 is actually greater than this. So it's got to be minus 1 is less than x, and then it's going to be less than the greatest value here. So root 41 minus 5 over 2. What I haven't quite figured out is why when we factorized it, we actually had a 1 here, and now I've got a slightly different answer. Just putting that into my calculator gets me, this becomes 0.7-ish. So yeah, I haven't quite got my head around why over here we had these two conditions which actually made it valid between minus 1 and 1, but with the second effort, it's not actually valid at, say, x equals 0.9. In I'm not going to worry about that in any case. In either case, or in this case as well, we still are then left with x valid. So therefore, valid. And if anyone watching this, it can tell me why we get slightly different outcomes with method 1 and method 2. I'd be really interested to hear it. Okay, that takes us finally to part D. We're asked to use the result from part B. And that was the, let me just bring that back down. The result from part B was this bit here, to estimate this integral. Okay, so I can say, if I define this to be I, then I can say that I is going to be approximately the integral from minus a half to a half of not this, but my new function. And this is another, it's really nice, this application of the binomial expansion. Okay, now you can work your way through that. It's a little bit technical. I'm going to give you a few shortcuts that you may or may not have seen before. This function here, 5 over 4x, is actually, it looks like this. It's actually called an odd function because it's basically if this, like if x was equal to 1, for example, I'd get 5 over 4. And then if x is minus 1, I get minus 5 over 4. So f of x is actually equal to f minus, sorry, I made a little mistake there. F of minus x is actually equal to minus f of x. The same is true for sine. Sine is an odd function. Antisymmetric is another name. But what that means, most importantly, is if I integrate it between two values that are the same, and it only works if they're the same, then my integral here will be will be the negative of my integral here. So I'm saying that these are just going to cancel out, and I don't even need to work it out. Exactly the same is true for this function. The cubic function is an odd function. So that's a nice little thing you can do to make it simpler. And you can take it even a step further, because for even functions, let's say I just take the x squared part of it. I know it's a minus x squared, but okay, if I just go with x squared for the moment, if I was integrating between, say, 3 and minus 3 x squared, then in fact, these two areas are the same, and I can just integrate from 0 to 3 and then double it. So that is a property of even odd functions. You can just cancel them out if you're integrating between plus and minus some value. Even functions, you can just double it. So I can make it 2 times the integral from 0 to a half of 2 minus 9 over 64 x squared, and just make my life so much easier. So this becomes 2x minus, now I'm going to be dividing through by 3, so I'll get 3 over 64 x cubed, evaluated at 0.5. And the other great thing in this case, when I put 0 in, is that it's all going to cancel out rather than having to deal with minus a half. I just ignore those terms. So 2 times 1 minus 3 over 64 times 1 over 8, which becomes 1 minus 3 over 512. This is actually going to be 512 over 512, which is going to give me 509 over 512 when I subtract them, but I still need to times through by 2, which gives me my final answer, 509 over 256. Okay, so that's brilliant. One thing I overlooked was that I needed the expansion to be valid between minus a half and a half, but it is. That's what we showed in part C. So expansion valid. So you couldn't do this. Point is, you couldn't do this binomial approximation for all values of x if you wanted to integrate between minus 5 and 5, for example. Doing this won't give you a good result. But for small integrals, it's another little tool to find approximate values, because otherwise, I mean, I'm not saying, I think this one you could probably integrate it exactly. I can't think of quite how, but it illustrates the purpose that for integrals you can use binomial expansion or other approximations to find approximate values like quite quickly.